In the last lecture, we have seen that an event that looks simultaneous in one inertial reference frame may not look simultaneous in another inertial reference frame. Now, we will talk about time dilation. This is another consequence of Einstein's postulate of constancy of the speed of light in all inertial reference frames. So here is our experiment. This is our S prime reference frame. There is a person in a wagon, and you can see this person sends a light pulse up towards the ceiling, and there is a mirror attached to the ceiling, and the light pulse retroreflects from this mirror and approaches the source. So observer O prime sees the light pulse move up and down vertically, a total distance 2d. There's a distance d between the source of the pulse and the mirror. So total distance traveled by the pulse is 2d, d up and d down. Now, there is an Earth observer. This is in the S reference frame. Observer O sees the light pulse move on a diagonal path. Why? Because the S prime reference frame is moving with velocity v. And this observer measures a distance greater than 2d for the light pulse. So if the total time of the travel for the light pulse is that's measured by the S frame observer is delta t, half of that time will be spent going up and half of that time going down. So the total distance traveled by the wagon in that time interval will be v delta t. So c delta t over 2, c delta t over 2, and we will see that we have this triangle forming. The vertical distance they measure is the same, d. C delta t over 2 is on one side when the pulse is going up to reach the mirror, and c delta t over 2 on the other side. And at the same time, the O prime observer has moved a distance v delta t over 2 in this reference frame. Okay, so what is the time of travel measured by this observer? Well, this observer has the same speed of light c, so total distance traveled is d plus d, 2d, so it's going to be delta tp, which is delta t prime, the time measured by the time interval measured by the S prime observer will be 2d divided by c. Okay, on the other hand, for the S frame observer, the Earth reference frame observer, we have this right triangle here, and we have c delta t over 2 squared, hypotenuse squared, is d squared plus v delta t over 2 squared. So this is basically going to let us know how much time passed. So in the S reference frame, when the light pulse reaches the mirror moved by v delta t over 2. Delta t is the time required for the flash of light to return to O prime as measured by an observer at O. This is our S reference frame. Okay, so from this equation, the Pythagorean theorem, we have delta t squared, parentheses, c squared over 4 minus v squared over 4 when taken to the left-hand side is d squared. So delta t turns out to be 2d divided by square root of c squared minus v squared. Since the time of this event was measured to be 2d over c by the S prime observer, we have 2d over c divided by square root 1 minus v squared over c squared. So I divide the top by c and bottom by c. C enters the square as c squared, so we're going to get square root c squared minus v squared divided by c will become square root of c squared over c squared minus v squared over c squared. So this is what we get for the time interval. So you see, for the total travel time of the light pulse, the S prime observer measures 2d over c, the S observer measures 2d over c divided by square root 1 minus v squared over c squared. So this factor, correction factor, in going from S prime reference frame to S reference frame is the relativistic correction factor. We call that gamma 1 over square root 1 minus v square over c square. So this v is less or equal to c, and therefore we see that this gamma correction factor is greater than 1. For v is equal to 0, it will be equal to 1, so greater or equal to 1. Then our delta t will become delta tp, the time interval measured by the s prime observer, divided by square root of 1 minus v square over c square, or since we have defined 1 over square root 1 minus v square over c square as gamma, gamma times delta tp. All right, and gamma is greater than 1. So the delta t measured by the S observer is greater than the delta t measured by the S prime observer. So what is this telling us? The time interval delta t measured by an observer moving with respect to a clock is longer than the time interval delta tb measured by an observer at rest with respect to the clock. So who is at rest with respect to the clock? That's the person inside the wagon, and with respect to the clock, the Earth observer is moving, so that observer will measure a longer time. This effect is called time dilation. All right. Now, if you concentrate on this gamma relativistic correction factor, for a speed of 0.1 c, if the wagon was moving at 0.1 c, we calculate gamma to be 1.005. So that's corresponding to 0.5% time dilation. So we have to get really close to the speed of light in order to observe these effects. Therefore, this effect is not observed in everyday life. So if you plot gamma as a function of v, you can see that an appreciable deviation from 1 occurs for only speeds very close to the speed of light. So you can see that usually we can neglect this relativistic correction, but when the velocity is approaching close to the velocity of light, we will have an appreciable relativistic correction factor. Now, this delta t measured by the S prime observer is called the proper time interval. It is the time interval between two events measured by an observer who sees the events occur at the same point in space. So is that true? The light pulse leaves the source and returns back to the source. So the source location is the same with respect to this S prime frame observer, so that's not changing. So the time interval between an event initiated at the source and finalized at the source at the same point in space, therefore this observer is measuring the proper time. But for this observer, this event started at this position of the source, initial position of the source, and final position of the source is a distance v delta t from the initial position. Therefore, this observer is not measuring the proper time. All right. So light pulse emission point and return points are the same for the S prime observer. So a moving clock is measured to run more slowly than a clock at rest by a factor gamma. So we have a clock that is moving with respect to this observer. So this observer will observe this clock to run slower than a clock at rest by a factor gamma. This is our time dilation effect. Now, do we have any experimental evidence for this effect? There is one experimental demonstration, that's the muon lifetime. So cosmic radiation causes atoms in the basically hits the atoms in the upper atmosphere, and those are muons created by this interaction, and the lifetime of a muon as measured in the reference frame of the muon is 2.2 microseconds, and muons move at a speed 0.99 c. Therefore, in the reference frame of the muon, 0.99c multiplied by the proper time. So the creation and annihilation points are at the same point in the reference frame of the muon. So we have 2.2 microseconds multiplied by 0.99c gives us 640 meters. They are created in the upper atmosphere, and therefore muons should never be able to reach the Earth if we look at it from the muon's point of view. However, if we look at it from an Earth observer point of view, this lifetime is corrected by a relativistic correction factor gamma, and since the speed is quite close to the speed of light, we find that the actual lifetime measured by an Earth observer is 16 microseconds. So 0.99c times 16 microseconds give us 4.8 kilometers, and muons reach the Earth's surface. And therefore, we see that the muon lifetime is a direct evidence for the relativistic corrections we should take into account, because we do detect muons reaching the Earth's surface. All right. So here is an example. What is the period of the pendulum? The period of a pendulum is measured to be 3 seconds in the reference frame of the pendulum. What is the period when measured by an observer moving at a speed of 0.96c relative to the pendulum? So here is our pendulum. How do we measure the period of a pendulum? So the pendulum starts at point A prime, goes to B prime, and comes back to A prime. So we basically see that the start and the end points are the same, so that's A prime. So who is measuring the proper time of this event for the period? That is the observer in the reference frame of the pendulum. So basically we see that the same point is the start point and end point in the reference frame of the pendulum. So delta Tp, the proper time, is 3 seconds, and the pendulum is moving at a speed of 0.96 c relative to the observer. This is our S prime reference frame. So the observer at rest, that's the Earth observer, sees time dilation. So gamma times the proper time interval delta Tp. So we have to calculate this relativistic correction factor gamma, which is 1 over 1 minus v square over c square. So it's going to be 0.96 c square over c square square root multiplied by 3 seconds. So this gives us, for the time interval delta t, 10.7 seconds. It's quite different from the proper time interval. And once again, this periodic motion begins at A prime in the reference frame of the pendulum and ends at A prime in the pendulum frame. Therefore, the pendulum must be measuring the proper time interval. All right, let's look at one more example. How long was your trip? Suppose you're driving your car on a business trip and are traveling at 30 meters per second. That's quite small compared to the speed of light. Your boss, who is waiting at your destination, expects the trip to take 5 hours. When you arrive late, your excuse is that the clock in your car registered the passage of 5 hours, but that you were driving fast and so your clock ran more slowly than the clock in your boss's office. If your clock actually did indicate a 5-hour trip, how much time passed on your boss's clock, which was at rest on the Earth? Okay, so the person driving in the car is basically recording a start point and end point. The start point and end points are the same because we are in the same point in the car. So the proper time interval, delta Tp, is 5 hours. The car observer is in the proper reference frame. Because in this reference frame, the start point and end point are the same. They are the same point in the car. End point is equal to the start point in the car. Okay, so that's the first thing. We have to determine who is recording the proper time. So the bus is recording an improper time, which is relativistically corrected gamma times delta Tp. Now we have to calculate this relativistic correction factor. It is 1 over 1 minus 30 meters per second, 30 squared divided by c squared, which is 3 times 10 to 8 meters per second squared, square root, multiplied by 5 hours, the proper time interval. Okay, so we will have a correction factor 1 over 1 minus 30 squared becomes 9 times 10 to 4. C squared becomes 9 times 10 to 16. So this is 1 times 10 to minus 14 square root multiplied by 5 hours. So this will give us, because this is such a small number here, 1 minus x to the power 1 over minus 1 over 2, where x is much less than 1, is basically 1 minus 1 times 10 to minus 14 to the power minus 1 over 2 times 5 hours. So we can think about the Taylor series expansion of 1 minus x to n. So let's record this review here. 1 minus x parentheses to the power n is approximately 1 minus nx when x is much less than 1. This is the Taylor series expansion. First you substitute x equals 0, you get 1, and then you take a derivative n times 1 minus x to the power n minus 1. You substitute x equals 0. This will give you just 1, so n multiplied with x. So this will be 1 minus nx. Taylor series expansion. All right, so this is basically something we know very well from Taylor series expansion, and therefore I can estimate the result. This will be, so my n here is minus 1 over 2, so it's going to be 1 plus 1 over 2 times 10 to the minus 14 multiplied with 5 hours. So this gives me 5 hours plus, let's convert the hours to seconds here, 5 hours, 60 minutes, 60 seconds, divided by 2 times 10 to minus 14 seconds. So I find that the time interval measured by the bus should be 5 hours plus 0.09 nanoseconds. All right. So what is the conclusion? The difference in these two clock measurements is negligible. So the difference is negligible. Therefore, this is not a valid excuse. Okay, so you can fool your boss if the boss does not know relativity. Okay, so let's summarize. We talked about time dilation effect. Time dilation effect basically is the fact that a moving clock seems to run slower than a clock at rest. If you look at this experiment where we send a light pulse up and down from the moving reference frame point of view, the time interval is 2d over c. From the reference frame at rest, S frame point of view, the time interval is determined by basically this right triangle here, and it's based on the fact that the time intervals are different because the speed of light is the same as measured by the S' observer. This is basically S frame observer says the speed of light is the same because of the postulate of Einstein, constancy of the speed of light. We have this right triangle, and this tells us that delta t is delta Tp multiplied by gamma. So what do we mean by delta Tp? Proper time interval. Proper time interval is the interval measured by an observer at rest with respect to the clock. And this person basically will record the event to occur at the same point in space. So the two events, the start point and end point, should be the same point in space with respect to this observer. Once we find the proper time interval, we multiply it by gamma to find the time interval measured by the person that is watching the event from the Earth reference frame. The moving clock, that is the clock that is attached to the proper time interval, is measured to run more slowly than a clock at rest by a factor of gamma, time dilation effect. But this gamma factor, which is 1 over square root 1 minus v square over c square, is greater than 1, and it's basically deviation from 1 is significant only for speeds that are close to the speed of light. So therefore, we don't observe these effects in our everyday life. And we have one example, basically a drive. So a person was on a business trip traveling at 30 meters per second, and the person expects the trip to take 5 hours, but the boss basically sees that the person arrives late, so the driver comes up with this excuse that there's a relativistic correction between the clocks. But you see, when 30 meters per second, which is much less than the speed of light, is considered in the relativistic correction factor, the time dilation correction is 0.09 nanoseconds, which is negligible. Experimentally, we see the muons created and annihilated in the atmosphere. They have a lifetime. Because they are created in the upper atmosphere, they have to travel quite a large distance to reach the Earth's surface. The muon lifetime measured in the muon reference frame is 2.2 microseconds. With the speed 0.99 c, they shouldn't be able to reach the Earth's surface, but it's the Earth observer who is basically measuring the muons, and they reach the Earth's surface because of time dilation effect. Gamma times 2.2 is 16 microseconds, and the distance traveled is 4.8 kilometers. Another example we considered was the pendulum. This pendulum is moving with respect to an observer at a speed 0.96 c. So the pendulum reference, in the pendulum reference frame, the periodic motion is occurring at the same point in space. So if you have an observer attached to this pendulum, we always measure the same start point and end point for periodic motion. So therefore, this period measured by the pendulum reference frame observer is the proper time. Multiplying it by gamma, we find the period reported by an observer at rest, or an observer moving at a relative speed of 0.96 c with respect to the pendulum. All right. So this basically concludes our discussion of time dilation, and next video we're going to discuss another important consequence of Einstein's postulates, that is the fact that we have length contraction. So the length contraction will come into play when I explained the simultaneity effect not being an absolute concept and it depends on the reference frame, I said this effect is not only due to transit time based on the arguments I have made here. Actually, the lengths reported by the observer at rest and observer attached to the primed reference frame are different. So there is a length contraction effect which also comes into play and results in simultaneity not being an absolute concept.